In this video, we're going to take a look at the calculation to determine the amount of water in soda crystals. So for this experiment, we would have titrated a standardized solution of hydrochloric acid with a solution made up of our soda crystals. So the first thing that we would like to find out from all of this information that we've gathered from our experiment is how many moles of our HCl have we used. Okay, so if I have a 0.1 molar solution, so I'm taking this piece of information down here, I have a 0.1 molar solution, and how much of it have I used? Well, what we're looking for there is the average titer. So we've 12.6 centimeters cubed. So what I need to do is I'm going to put a little heading for myself, and you will find that writing these little headings will help you. So I'm going to write moles of HCl. So they'll help me to just keep track of what have I just figured out and when am I going to use it again. I can find it very quickly. So moles of HCl is going to be, well, I know molarity, so I'm just going to write down what I know. Molarity is 0.1 moles per litre. So if you like using your dimensional analysis, you can write your units out. So moles per litre. And the other thing we knew was we knew the volume. Now, if this is in litres, I would like my volume to be in litres as well. So what I'm going to have is the average titer, which is not 12.6, apologies. It's actually 12.55. So I'm going to take that. So that's my volume being brought down here. That's 12.55 centimetres cubed. If that's in centimetres cubed, then I can turn it into millilitres. It's just that, millilitres. And then remember our trick. If I know it's milli something, I can change the m out for this by 10 to the minus 3. And that tells me then how many litres I've used. Why did I need litres? Well, if I'm dealing with moles per litre, I need to have my volume in the litres unit as well. So now I'm going to see how do those two combine. So I have 0.1 moles per litre. I will be using that, and I want to get to moles. So then I need to figure out, to get rid of this litre on the bottom, what do I need to do? Well, if it's on the bottom, it's divide. So ideally, I would like to have something that multiplies and introduces the litre up here. And that's where I'm getting that from. So it's my volume times my molarity. So there is the volume that I've used. This is the molarity per litre. And when I do that then, I'm actually going to leave a little bit more space. When I do that, I get 0.001255 moles. And just be careful with your notation here, and when you're documenting your answers, that you don't drop a zero, because that'll have a huge impact later on. That's the number of moles of HCl that we had, that it took to get us to the point of neutralization, or the end point of our titration. Now I need to figure out, right, how am I going to use this information to figure out the moles of Na2CO3? So now we need to figure out that. The moles of Na2CO3, which is the active ingredient in those soda crystals. That's what's doing the cleaning for us. How am I going to find that? Well, I need the balanced equation. So I'm going to write out the balanced equation so that we can see. It's Na2CO3 HCl. But there's 2 HCl's required to bring this reaction to the neutralization point. 2 NaCl are produced. We get water, as always, salt and water. But because this is also a carbonate, we also get carbon dioxide gas. Now I need to figure out, okay, if I know the moles of HCl, what is the ratio of the HCl to the Na2CO3? So what I actually have, look, is I've got one of them. So I can write 1. So the ratio of Na2 to CO3, Na2CO3, the ratio of that to HCl is going to be 1:2. So if I have, from above, let's just take that down here, this many moles of HCl, I should have half as many. I should have half as many as I do here. So when I divide that then by 2, what I will get is that the moles of Na2CO3 will be 0.0006275. And that there represents the number of moles of Na2CO3. And again, I like to write lots of little notes, lots of little comments next to what these numbers are, so that when I have to use it again, I can pull it up really quickly and I know what I'm doing. It's also just in case I get distracted mid-calculation, I look up at the clock, somebody asks me a question, and then I lose my place. I don't have to start all over again or trace too far back. I can find things really quickly because they've all got labels. What can I do with that moles of Na2CO3 then? Well, I can convert that into a mass. Normally what we would do is we would like to get it in the moles per litre to calculate the molarity of it, but this calculation is different to the other 3 calculations we would have done for the other titrations, because what we're actually trying to work out is, in the soda crystals, what percentage of it was water to make the crystal and what percentage of it was the sodium carbonate. That's what we need to figure out. So we're now going to try and convert this into a mass, because to do that we know how much mass we had to begin with. So if I could figure out what mass I have that is the active ingredient, and I know how much I measured out at the start on the clock glass, then what I can do is I can subtract them and I know what the mass of the water is. So what I'm going to do now is I'm going to get the mass of Na2CO3. Now, what I'm thinking is, right, I know the moles, so I'm just going to copy and paste it down so I don't lose any zeros. This is the number of moles that I have. I need to now think about what is the connection between moles and mass, and you should be getting really good at it at this stage. Connection between moles and mass is molar mass. So I need to figure out the molar mass of Na2CO3. How am I going to do that? Well, I'm going to have 2 by Na plus 1 by carbon plus 3 by oxygen. So I'm going to have 2 by 23 plus 1 by 12 plus 3 by 16. And where I'm getting those from, those are the masses of those elements on the periodic table. When I do that out and I add them all together, I get 106. And remember, molar mass has the formula grams per mole. You can write it as 106 G/mol. I like to write it like this because it really helps me to spell out to myself what I'm doing in the next few parts of the calculation. So I've just gotten the grams per mole and I want to turn it into grams. That's what I want to figure out. So I'm going to write out 106 grams per mole. How do I convert that into just grams? Well, I want to get rid of the moles, so I'm going to have to multiply it by something that has the number of moles, which is up here. So there's the number of moles that we have. I'm just going to shrink it down so it fits in for us. And we can make it bigger now again. But if I multiply those two things out, then I will get the number of grams that I have that reacted with the HCl. So what was the active ingredient? How much of it was there in it? So when I multiply those two things out, I get 0.0665 grams. So 0.0665 grams. So that tells me that in the sample that we have in our conical flask, so when I had the reaction inside the conical flask here, I now know that when it got to the point of completion, there was 0.0665 grams of Na2CO3. But you might remember when we actually had to make up the solution with the washing crystals, it wasn't the same amount as was in the conical flask, because you actually made up more. You actually made up a solution of 250 centimeters cubed. So when you weighed out at the start on your clock glass and you had your little crystals here and you weighed that out, you had 1.57 grams, I believe. Let me just check that. Yeah, 1.57 grams. You then took that 1.57 grams and you've put it into a volumetric flask that was 250 centimeters cubed when we filled it up so that the meniscus sat on the line when we looked at it at eye level. So that's 250 centimeters cubed. So what you had was 1.75 grams in 250 centimeters cubed. But then what you did was you didn't use all of that in your titration. You actually took a sample of that out, and that sample you took out, you poured it into a beaker, and then from the beaker you would have used a pipette to take out 25 centimeters cubed of that. And that then went into, so that's 25 centimeters cubed, that went into our conical flask. So what I actually know is that if there were 0.0665 grams inside in the conical flask, if I wanted to find out how much there was in the original solution, I would have to account for the fact that I had 1/10 the amount inside here, because the dilution factor went from 250, we went from 250 to 25 centimeters cubed. I took a slice of that. I took a tiny piece of the 250 centimeters cubed. So if in 0.0665 grams is in the 25 centimeters cubed, to scale it back up to the size that it is originally in the volumetric flask, we have to multiply it by 10. So I'm going to now go 0.0665 multiplied by 10, and that's to find out how much there was for us originally. So I get 0.665 grams. So that tells me that of the original amount of crystals that I weighed out, the 1.57 grams, of that amount, 0.665 grams of it is Na2CO3. The rest of it is water. So now what I want to do is figure out the amount of water. So we're going to go mass of H2O in our soda crystals. So what I have is I know that I originally weighed out 1.57 grams, but I know of that 1.57 grams that 0.665 grams of it is actually sodium carbonate. So this is the water and sodium carbonate. I figured out by titration how much sodium carbonate there was in it. Now I'm going to subtract it, and the only other thing inside of it is assumed to be the water. So I'm going to subtract those, and I get 0.905 grams. So that's how many grams of water are inside in the original crystals that we weighed out. Now what I can do is get a percentage of the amount of water that's present. So I'm going to find out percentage-wise percent of H2O in the soda crystals, which has a formula like this: Na2CO3, and then it has an XH2O. The X is there for us right now because we don't know how many waters there are per Na2CO3. We'll be able to figure that out in a moment, but you might be asked or you might be looking to find out what percentage of it is water. So I'm going to give us space, move this down here. So if you want to figure out the percent of anything, then you're going to put the amount of water, which is 0.905 grams. You're going to put that all over the amount that you originally weighed out, and you're going to multiply that by 100. So this is giving us again the percentage of water in our soda crystals. If I do that out, I actually get out 57.64%. So that's the percentage of water. Now, on to the next part. I need to find out, what is that X? How many times more water particles are there in the crystals that we weighed out are there versus the sodium carbonate? So what I need to really do that, if I'm talking about this formula, Na2CO3, and if there's an X here, so we're going to say X H2O, that's the number of moles of water. Okay, so what I actually need to do is calculate a ratio of the moles of Na2CO3 versus the moles of H2O. So that is what I will need to calculate now, is a ratio. And that's what that X is it tells us how many times more H2Os are there than sodium carbonates. So I already know the moles of Na2CO3. We worked that out earlier on, and the number of moles we got out, if we go back up here, we had it, the moles, and this is where labeling them, look, becomes, a really handy tool and skill to have. That's how many moles I had. And it was really quick to find because I'd labelled everything correctly. That's how many moles of that. Now I need to find the moles of water. I don't know the moles of water, but I do know is I know the mass of water. We knew the mass of water was 0.905 grams. How do I go from grams into moles then? What's the connection? And you might be thinking molar mass. So the molar mass of H2O, we need to figure that out. So it's going to be 2 times the hydrogens, because I've got 2 of them, plus 1 times the oxygen. That's going to give me 2 by 1 plus 16, and so I get 18. And remember, molar mass has a formula that is grams per mole. Now I need to figure out, how does this combine with this? Do I multiply or do I divide? So I'm going to write down what I have for sure. I've got 0.905 G, and then I'm going to say that what I want over here is I want the moles. So I want the moles to be on top, and if I want the moles to be on top, then what I do is I divide, because what happens when you divide by a fraction is you keep it you keep this sign, you keep the first one the same, 0.905 grams. You change this to multiply, you flip the fraction. And now what will happen is our grams will drop out. So you keep, you change, and you flip. So now what I'm going to have, if I do that out for us, it's going to be 0.905 divided by 18, and I get 0.05028 moles of H2O. So keep up the labelling. That is our moles of H2O, and remember I wanted to get a ratio of the two of them versus each other. So I'm going to have 0.00, let's just copy and paste it down so I don't drop any zeros. I'm going to take this down here. I want to know if that's our Na2CO3. What is the ratio of that to the water? So I'll write it above. Na2CO3 is to the water moles. So 0.05028. So we're now going to have to divide to find how many times bigger the water is. So we're going to see how many times does this fit into this. So 0.05028 divided by 0.000625. If I do that and I divide it in, I get 8.01. So that tells me that there are 8 times as many water particles as there are our sodium carbonate. Now, how do I represent that in terms of the formula? Well, remember, we were looking to find out if we had Na2CO3 times X amount of waters. We now know that that X is what we just found out. So it's Na2CO3 and there's 8 times as much water. So that there is how we would work out how much water there is in the soda crystals.